In Germany, researchers are developing a truly remarkable innovation, a cold storage system that quite literally captures winter's chill and uses it to cool buildings during the summer. It sounds like science fiction, but it's not. Scientists from a research institute have teamed up with engineers from a private company to build a seasonal cooling system that stores cold underground, dramatically cutting the energy used for air conditioning. And we're not talking about small gains here. We're talking about a potential 70 to 90% reduction in electricity demand compared to conventional systems. Even more impressive, if widely adopted, this technology could save up to 20 million tons of CO2 emissions per year in Germany alone. This type of design could reshape how we think about cooling systems, not just in industrial facilities, but eventually in homes as well. So, how does it work? Where is it being built? And could this cold storage technology become part of your everyday life in the future? Let's break it down. The demand for cooling in Germany is already substantial. About 14 to 15% of the country's total electricity consumption goes directly toward refrigeration and air conditioning. One-third of that comes from households, things like refrigerators and air conditioners. But the majority, nearly two-thirds, is driven by the commercial and industrial sectors. These include climate control systems in office buildings, cold storage in supermarkets, and specialized industrial cooling processes. Most of this cooling is handled by what's known as compression-based refrigeration. These systems use a refrigerant that cycles through various pressure and temperature states to move heat from one place to another. This is the same basic principle behind your household fridge or the air conditioner in your car. While effective, these systems are extremely energy-intensive and often rely on refrigerants with a high global warming potential. In fact, air conditioning systems in Germany alone are responsible for more than 3 times the CO2 emissions of all domestic flights combined. And this is in a country where most buildings still don't have air conditioning. As global temperatures continue to rise, the need for cooling will only increase, bringing with it even higher energy consumption and emissions. To address this growing challenge, researchers and engineers have joined forces to design a new kind of cooling solution. One that doesn't just shift heat around, it stores cold. It's part of a collaborative project aimed at industrial energy savings, but with the potential for much broader applications. Let's say you're running a high-tech lab or a battery testing facility. These types of operations generate a lot of heat, and they need precise year-round cooling to function. Traditionally, this is handled with a combination of free cooling, drawing in cool outside air at night, and energy-hungry compression systems during warmer periods. But free cooling systems often produce more cooling power at night or during the winter than is actually needed at that moment. And up until now, that excess cooling has gone to waste. That's the opportunity this new project aims to capture. The system centers around what's known as a subsurface cold storage field. Think of it as a thermal battery, but instead of storing electricity, it stores cold. And instead of using high-tech materials or chemical reactions, it uses the Earth itself. Here's how it works. Engineers drill dozens of vertical boreholes deep into the ground, up to 100 meters below the surface. Inside each borehole is a closed loop of pipe filled with a brine solution. This fluid can absorb heat or cold and transfer it to or from the surrounding rock. During the colder months, when outside air is cool and free cooling systems are running at high capacity, the system uses that surplus cold to chill the brine, which then cools the ground around the boreholes. Essentially, they're freezing a section of the Earth. Later, when the weather heats up and cooling demand spikes, like on a hot summer day, the system reverses. The brine absorbs the stored cold from the chilled rock and carries it back up to the surface where it's used to cool the building or lab. What's remarkable about this approach is that it decouples cooling from energy-intensive compression and instead uses passive heat exchange. The rock at 100 meters deep maintains a relatively stable temperature year-round, around 11 to 13 degrees Celsius. But by using winter cold, engineers can push that temperature even lower and turn the ground into a powerful seasonal cold reservoir. This concept isn't entirely new. Borehole thermal energy storage has been used before for heating, but using it in reverse for cooling at this scale with intelligent control over temperature flow is where this project breaks new ground. The project has already passed the feasibility stage, and now a pilot system is being installed at a facility known for its energy-efficient test labs. This site is particularly ideal because it operates battery testing and validation systems for the automotive industry. These labs generate significant heat and require constant cooling, around 300 kilowatts on average, with peak loads reaching up to 420 kilowatts. To meet this demand, engineers installed 35 boreholes at the test site, each drilled to a depth of around 100 meters and spaced roughly 5 to 10 meters apart. This underground network forms the core of the cold storage system. The total storage capacity of this thermal field is estimated at 366 megawatt hours, enough to cover about 15% of the facility's annual cooling needs. That might not sound like a lot at first, but it's specifically designed to handle peak cooling loads. During moments of highest demand, like during equipment stress tests or heat waves, the system can deliver up to 550 kilowatts of cooling power. That's more than enough to meet the facility's maximum requirement without switching on energy-hungry compressors. And that's where the magic lies. While the system may not yet handle year-round cooling independently, it drastically reduces the need for active mechanical cooling during high-demand periods. That alone can lead to enormous energy savings. One technical challenge with borehole systems is that they're usually designed to deliver steady, continuous output, not rapid fluctuations. But industrial cooling needs aren't always steady. Sometimes demand spikes quickly. To solve this, the team designed a unique configuration that allows for dynamic performance. The boreholes are connected using a dual-loop system, a distributor and a collector, allowing the brine to flow through different boreholes in series or parallel, depending on current needs. This flexible routing allows the system to control how much cooling is extracted from which parts of the field and when. It's an elegant way of turning a passive thermal system into a responsive, on-demand cooling network. The result? A passive, intelligent cold storage solution that's unlike anything else currently in use. According to the engineers, this design could reduce electricity consumption for cooling by 70 to 90% annually, without relying on traditional refrigerants, which are often environmentally damaging. So, what's next? The pilot project is moving forward. Construction of the system began in late summer with full deployment and monitoring expected by early next year. Once it's operational, researchers will study its real-world performance, including its responsiveness to fluctuating demand, its long-term energy savings, and its scalability. And this is where things get really exciting, because while the current project is tailored for an industrial setting, the underlying principles are applicable elsewhere. In theory, a modified version of this system could be used for residential buildings or public facilities like schools, libraries, or hospitals. Anywhere that experiences seasonal cooling demand could potentially benefit. Of course, there are some caveats. The effectiveness of the system depends heavily on local geological conditions. The subsurface temperature, the type of rock, and the natural conductivity of the soil all play a role in how well the system performs. Fortunately, much of Germany is well suited to this kind of installation, and many regions already have online databases showing suitability for shallow geothermal systems. Another consideration is cost. Because the technology is still in the pilot phase, it's difficult to predict how economical it will be at scale. Factors like construction costs, energy prices, and system utilization all affect the return on investment. Also, a digital twin, essentially a real-time virtual model of the system, still needs to be finalized to fully simulate and optimize its operation. But despite these unknowns, this project represents a promising leap forward in sustainable building technology. It's an example of how we can take natural environmental conditions, cold winter air, and store them for use during times of peak need. It's low-tech in some ways, but extremely clever in execution. And as climate change drives up global temperatures, solutions like this could play a major role in reducing the cooling sector's carbon footprint. Even in a temperate country like Germany, the need for summer cooling is rising, and cities and buildings are starting to feel the strain. Being able to cool spaces without massive energy bills or emissions is becoming not just desirable but necessary. By combining traditional ideas like seasonal thermal storage with smart control systems and modular design, we might be able to build a future where homes, factories, and offices stay comfortable using stored winter cold instead of year-round electricity. If the pilot project succeeds, it could be the blueprint for an entirely new generation of sustainable cooling systems. Let's see how it develops.